So today we will take up another oxidizing agent, selenium dioxide. Selenium dioxide is used for the oxidation of reactive methyl and methyl compounds to give dicarbonyl compounds. So I write here, selenium dioxide is used for the oxidation of for the oxidation of reactive methyl and methyl compounds, methyl and methyl compounds to give to give to give dicarbonyl compounds. Okay, dicarbonyl compounds, carbonyl compounds. Okay, so I'm writing so I'm repeating again. Selenium dioxide is used for the oxidation of reactive methyl and methyl groups to give dicarbonyl compounds. Say, suppose for example, say this type of reactive methyl groups. Another one is another reactive methyl groups. So they are reactive because of the presence of the carbonyl groups. So when it oxidize selenium dioxide, so more than the presence of water. So here two same case. So here these methyl groups are oxidized to these aldehyde groups, and these groups are, let's say this another one. Okay, I'll write down this one. Let's say another phenyl groups. Let's say another substituent. Okay, I'll find like this, or you can say simply you can write this way. Okay, this is methyl groups and reactive methylene groups. This is methylene group, and this one is methyl group, reactive one. They are very reactive because of the presence of the carbonyl group. Next to the methyl group, there are carbonyl groups. So here methylene to carbonyl group. So when you oxidize with selenium dioxide in presence of water, this methyl group is oxidized to the aldehyde group, and the methylene groups are oxidized to this ketonic group. Okay, so we got so we can say dicarbonyl compound. Here also you can say aldehyde groups. Dicarbonyl compounds are obtained. I'm repeating again. Selenium dioxide is mostly used for the oxidation of reactive methyl and methyl groups to give dicarbonyl compounds. So I'm giving examples. Say this is here COCH3, this methyl group is reactive as compared to the presence of carbonyl group. So when you oxidize with selenium dioxide, you get this aldehyde group. And when is a reactive methylene group reacts with the same compound, selenium dioxide in presence of water, so we got a ketonic group. So we got dicarbonyl compounds. So this is selenium dioxide. So it is available, selenium dioxide is available commercially, but it can be prepared also by heating in the air at high temperature. So it is available commercially, It can also be prepared by heating selenium metal, by heating selenium in presence of air in presence of air, selenium very strongly in red hot, strongly in air, in the presence of air, in the air. So we can get selenium in presence of oxygen, very red hot, heating by red hot. Okay, very high at high temperature. So you got selenium dioxide. It is very simple. It is mostly used. Selenium dioxide is mostly used as a solution in acetic acid or water or ethanol, or in presence of dioxane. It is used. Selenium dioxide is used most commonly in in acetic acid or as a solution in acetic acid, aqueous acetic acid, or dilute acetic acid, acetic anhydride, and the water, alcohol, etc. in presence of dioxane, Okay, so mostly it is in solution forms. So when water reacts with selenium dioxide, water it gives selenous acid. Selenium dioxide in water it gives selenous acid. So the reaction takes place generally like this. Always. Okay. This is called selenous acid. So it is commonly it is the one attacking the reactive methylene groups. So it is, you can write this one, H2SCO3. Okay, this is the formula. So here in mostly this reaction takes place by reacting with selenous acid. So using selenium dioxide, in the case of oxidation, selenium dioxide is reduced to selenium, okay, metallic selenium. Then it's from red to here it is red. So I write here. So selenium is when the reaction takes place, selenium dioxide is reduced to selenium metal, okay. So here red to black. So the black solid mask. So here selenium dioxide is red in color. So when reaction takes place, it comes to black selenium. Okay, this is red in color. So let's see how the reaction takes place. So I'm give some examples of oxidation of this reactive methylene groups by selenium dioxide. I'll give some examples. So for example, acetophenone. Let's say acetophenone. When it reacts with this selenium dioxide in presence of water, or in presence of water and dioxane as a solvent, so this will come to phenyl CO, so active methylene plus selenium solid metal, okay, it is black in color. So this acetophenone is oxidized with selenium dioxide in presence of water, so to this compound. So here similarly acetaldehyde, when it reacts with selenium dioxide, water and dioxane, so in same case by heating, so it will come to CSO, this is going to say glyoxal, okay, this is called glyoxal. So these methyl groups are oxidized to CSO group, aldehyde group. So now you can say another example, CH2 phenyl, okay. So here this is reactive methylene compound here. So so here you get selenium dioxide, water, same case dioxane. So you can have this phenyl CO, this reactive methylene group is combined to ketonic group, and phenyl like this. Because this is called dicarbonic compound. So this is benzyl, this is glyoxal, this is glyoxal, okay, glyoxal, and this is benzyl. So like this. Many examples are even cyclic ketones also can be oxidized. So like this, cyclic ketones, same reaction conditions. So it gives this dicarbonic groups, okay, like this. So here, so I'm giving some examples like this. So let's see the mechanism how. So I'm repeating again that this is methyl groups, reactive methyl groups. Here also reactive methyl groups and reactive methylene groups. And reactive methylene groups are oxidized to the carbonyl groups. So here reactive methyl groups are oxidized to aldehyde group. Here also reactive methyl group oxidized to aldehyde group, and here reactive methylene group combined to ketonic group. Here also reactive methylene combined to ketonic group. So let's see the mechanism of the selenium dioxide oxidation. Okay, mechanism of selenium dioxide oxidation. So here first mechanism. Same example we can take place here. Phenyl, formation of benzyl, NaCO, CH, reactive methylene groups, and then we have this phenyl, okay, another phenyl. So now react with selenium in water. selenium dioxide in water. Okay, so this will give selenium acid. So let us write selenium acid like OO, OS, and also OS. Okay, this is selenium acid. By reacting these two, we got H2 SCO3, selenium acid. So this is the one, this one. So first I converted this one, and then I take here. So then coming back, this is going back and coming back again, the loss is as water. Okay, so OS is lost as water. So minus, so you get past intermediate is this one, CO ring with SC, then double put this double bond O coming back, and then this OS there, OS. Okay, so this double bond here and CH and phenyl here. Okay, so first from this one, so it is again reacting again this conversion takes place again this one again like this. Okay, reaction. Another intermediate got phenyl C double bond O CH, then another phenyl, so O SC OS. Okay, so like this. So another intermediate, and finally this lost this one, so it gives ketonic group here, carbonic group, and then selenium, and then OS where it lost this one. Just pick up the water, there's a water loss. Okay, so you can have benzene now. Got 2 dicarbonyl. This is benzene plus selenium 8 plus water. Okay, so this is the mechanism. So I'm repeating again. So here we have reactive methylene compound reacts with this selenium dioxide and water. It gives selenium acid. The selenium acid reacted like this. So I take this O attack to selenium and O group, and coming back water lost as water. So we got intermediate this one, and again lost, it reacted like this and get this one. So another intermediate. So rearrangement takes place. These three chemotropy reaction takes place. So we got chemotropy reaction takes place. So we got this intermediate. Finally lost this as water. So we got a product. So this is benzyl. We got a benzyl. So this is about the oxidation of reactive methyl and methylene groups. So selenium dioxide can also be used for allylic oxidation. So I write down here another important useful of applications of another important application of selenium dioxide is the allylic oxidation. Allylic oxidation. So we have discussed earlier in the case of earlier cases oxidation of reactive methyl and methylene group. Now we will say allylic oxidation by selenium dioxide. So another important application of selenium dioxide is allylic oxidation. So here, for example, here I'll give you one example. Phenyl CH2, so it has CH double bond CH. Okay, there is another group phenyl. Okay, or let's say CH3. So when you use selenium dioxide water and reflux at high temperature in the presence of acetic acid in high temperature 115 degrees Celsius. So you got we got this fast compound, we got this acetic acid is used, so you can get CH double bond. So migration development takes place. So here CH, another CH here. Okay, CH, C. So here link up with the acetic acid is used, so we can have OCOCH3 style group, OCOCH3 and CH and phenyl group. Okay, you can see. Okay, so we got a product. We use acetic acid. And then hydrolyze this one with water, then you got a OH group. Water hydrolyzing this CH, CH, double CH, COH, CH phenyl. Okay, like this. So by hydrolysis, you got this allylic alcohol. So allylic oxidation takes place to keep the allylic alcohol. So let's say this is methyl group, then you can have CH3 here, CH3 methyl group. Okay. If you use phenyl, then phenyl will come. So let's see. I'm repeating again that these allylic groups, allylic reactive methylene groups are oxidized. So the rearrangement takes place to give this compound. Okay. So you can have this one also. You can have OH. It can become here also. by rearrangement of the double bond. So let's see the mechanism first. Mechanism of the reactions. Mechanism of the reaction. Okay. So here I'll write down here. So mechanism of the reactions. Mechanism of allylic oxidation. Okay, here. Mechanism of allylic oxidation. So first, let's say this compound like earlier one, phenyl, okay, CH, double bond CH, CH2, and methyl group. Okay, let's take the example earlier cases. So when you present it, selenium dioxide in water, selenium dioxide in water, reflux, selenium dioxide in water, acetic acid, reflux, okay, heat around at high temperature. First, so we'll get this one. So this is the methyl groups, hydrogen here. So we have this selenium, say O, OH, okay. This selenium acid. When selenium dioxide react with water, it gives selenium acid. So first step is like this. So I take this one here, then this goes and coming back again, and then lost this as water. Okay, I suppose this one pick up like this. The photon is transferred here. So loss of water. So we got as an intermediate, we got this phenyl, CH, and so the selenium here. So we got this OH here, this OH here, this double bond over here, and this becomes CH, double bond CH, and methyl group here. Okay, so we got this one like this. In the intermediate we got, let's say A here, this intermediate A. So this can get two ways. So when you water attacks here, so reacting by water, so you can have another one at water attack here. So you got this here, water attack here, water attack here, and then we got this selenium, okay, like this. Okay, so product will be phenyl, CH, OH here, CH, double bond CHMe. Okay, first if you use acetic acid, then acetyl group attack here, then hydrolysis, we got the same product. Okay, so we got another this product. Okay, again this one, if you this one A can undergo direct, this one rearrangement CH methyl. Okay, so let us say this one, this is the A. Okay, no, this one CH, SC, double bond O, SOH, double bond here. Okay, so this is the A, this compound A. So it can undergo another rearrangement like earlier cases. So you can undergo rearrangement to give this one like this. Okay, so here we got another intermediate. So phenyl, CH, double bond. So here CH, then CH, methyl group here. The link with this selenium, the link with O, SC, OH. Okay, OH. So here link with this one. So we got the link with the O link with it and CSOH. Okay, O link here like this. This become double bond. C double bond here, and this link this broken down here, so it comes like this. So this is how the hydrolysis. We got another product. By hydrolysis of this one we call phenyl, CH, 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 OH, methyl group. Okay. So we got another product. So this is another one product, another product we are depending allyl alcohol. This is also allyl alcohol, but the position of the bond is different. Yeah. Now OH is near phenyl here, but OH is near methyl group here. So the position of OH is different. So yeah, I'm repeating again for allylic oxidation of using selenium dioxide. So you have transferred this migration of this hydrogen takes place, attack to this, and with the loss of water, then again water attack this position, and selenium loss. So we got this product. Okay, similarly A can be again undergo rearrangement like symmetric rearrangement. So this can go another compound, and hydrolysis will give this OH compared to OH. Okay, so we got two types of allylic alcohol. So allylic compounds are oxidized to allylic alcohol by using selenium dioxide. So this is the mechanism of the reactions. Okay, and then the last one, say the tri-substituted, or you can say tri-substituted alkenes, double bond compound, olefinic compounds, can also be oxidized selectively at the more substituted end of the carbon-carbon bond. So I write down tri-substituted alkenes, the olefinic compounds are oxidized, can be oxidized by selenium dioxide, selectively, selenium dioxide, selectively, at the end of the more substituted carbon end, end of the carbon bond, more substituted end of the carbon double bond. So here we use trisubstituted alkenes, double bonds. Okay. So I'm repeating it. Trisubstituted alkenes can be oxidized by selenium dioxide in presence of water selectively at the more substituted end of the carbon double bond. So for example, let's say we have trisubstituted alkene. Okay, so compound C, hydrogen here, CH2, R. Okay, another one here, R. Okay, so we have tri-substituted 1, 2, 3 tri-substituted, and this is more substituted here and double bond. Here this carbon is more substituted and here less substituted. So when you oxidize with selenium dioxide in presence of water or selenium dioxide, so you can get another mechanism also. Okay, selenium dioxide. So first selenium attack here, double attack, so like this. So we got R, CH2, C, double C, ice, CH2, okay, CH2, R, then here R, so you got SC, here, double bond O, okay, that, oh, not this way, SCO, and the O prime here, okay. So we have got intermediate, and this one is, so here link this one. Here we can link this side, most substituted side is linked, okay. Most substituted side is linked. So here link with this one. So here positive charge here. So we can write this SC O is O double bond O negative charge, okay. So then you got this one, okay, first step. So this one comes double bond here, this loss of one proton. Okay, let us have one here, hydrogen here, attack here, so it is like this, CH2, okay. So we got first, we get R, CH, double bond, so you can see, okay, double bond C, CH, and then this R here, this becomes this CH2 here, then CH2, R here, then this is selenium, okay. You can write this way, we can write this way, okay, you can write better to for mechanism, okay, you can write this hydrogen here and selenium here, and this double bond here, O, and then this O negative, and O is double O like this earlier one. This become O negative here, and this O here. So link up this one, link up, this become positive charge. So link this one, this carbon link with this one, so it gets correct. Okay. So now this because the proton here, so we got this one. Okay. So we have here SC, and so the double bond here, then O is here. Okay. So we can write. So this product comes like this. Okay. Then rearrangement takes place. Symmetry rearrangement takes place. Attack here, then comes then like this. Okay. So symmetry rearrangement takes place to get this R, CH, O, SC, OS, okay. So that this is carbon links with this one. Then we got C double bond, then R here, then we have CH, CH2, R, okay. So it comes like this. So link up, this was broken down, so it becomes double bond here, then hydrolysis, we got a final product, okay. This hydrolysis, so I write down product here. So hydrolysis, this will give OH groups, Okay, so RCHOS, RCHOS here, OS, then you have CW1C, CH2, R, is R, okay. So this is the product. So like this hydrolysis to take water, so it goes like this. So you got this product. So like this is repeating again. Trisubstituted alkenes can also be oxidized by selenium dioxide selectively. Selectively when you oxidize this compound, this active methylene groups, this one CH2 groups is oxidized to R, okay, R, CH2R. Okay, this is the starting material. So I substituted 1, 2, 3 are substituted. So selectively oxidized at the most substituted end of the carbon atom. So you're not here. So reaction takes place. So by the other side, link with this, first link with this one, then again attack. So rearrangement takes place, symmetric rearrangement. So you got this product, and finally hydrolysis. So this active methylene group CH2 group is oxidized to alcohol. So this is about the synthetic applications of selenium dioxide. So selenium dioxide is used as an oxidizing agent for oxidation of reactive methylene groups, and also for allylic oxidation, and then trisubstitution also. So this is about today's lecture. So this is about today's lecture. So that's one of here. Okay.